erase what we were trying to get.
Yeah.
We're trying to show that this is equal to
H of x.
f prime of h of x.
X naught.
No, thank you. Okay. Let's think how we could do that. Maybe reverse engineer this for a second. So think about what this gives us.
That's f.
This gives us that the limit as x approaches x naught
Equals f of x minus
of f of
h of x.
I don't know if that's the right way to think about this, actually. It's going to, I think it's going to be this. Right? I think that's going to be using the definition correctly. F prime at a point is equal to the limit
The
as whatever our domain of f is. Our domain of f is h of j in this case. So I think going from here to here is the case. So all we need to do in our argument is basically argue that as x approaches x naught, h of x approaches h of x naught. So we know, here's what we're trying to evaluate, but we put before this, observe that since h is continuous, what does that mean?
The limit.
That means that, well, I'm going to go straight to, since h is continuous, comma, then the limit as x approaches x naught of h of x is equal to h of x naught. Right? Which gives us what we want. That gives us that the limit as x approaches x naught of h of x minus h of x naught is equal to 0.
Where did you get that 0?
You just.
The limit of this equals this. Subtract this from both sides, and I can take the limit of this if I want, because the limit of a constant is still just a constant. So I can rewrite this like that. Okay, so now I know that as x approaches x naught, actually I didn't even mean this. I mean this is exactly what it means for it to be continuous. I know that as x approaches x naught, h of x approaches h of x naught. So then this is equal to the limit as h of x approaches h of x naught of the same exact thing.
Yeah, I see.
Which is exactly what we have written up there, right? I'm going to rewrite this thing right here, right there, which is the exact definition of that. Okay, we're done.
Why do we have to use all of those?
We just need to use the fact that h was continuous. And we use the fact that this is differentiable, meaning this limit exists. So we're taking the limit of f, which obviously we can do. You follow the logic?
I don't know what we're trying to do with it.
Maybe I need to write this out more explicitly. So forget the side stuff over here.
Well, I follow the logic, I just don't know. Okay, now what?
Well, so we'll just finish spelling it out exactly. So, since h is continuous, then the limit as x approaches x naught of h of x is h of x naught. So, as x approaches x naught, h of x approaches h of x naught. So the limit as x approaches x naught is the same as the limit as h of x approaches h of x naught. So you're good with this. Now f is differentiable, which means this limit exists. And what do we call that limit? We call that limit f prime of whatever point we're taking it at, h of x naught. What did the problem say to do? It said prove that if this is the case and we weren't divided by 0 right here, basically, then this limit is equal to this. And notice we use this fact to get this, and then we use this fact to evaluate this. Good? Okay, so now they were saying use this fact to evaluate some limit in the next problem, right? So then we're looking at 7. What's the limit as h approaches 0 of this? Now, you already know how to take this limit.
What do you mean take it?
Just evaluate it. Okay, maybe not. So let's do it. So now we're assuming that f is differentiable. So we're taking the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h.
When it says f is differentiable at x naught, it's just saying that because it's just saying the limit exists at 1.
Sorry, say that one more time.
So when it says, I'm confused what it's asking us because it literally says that f is differentiable at x naught equals 1. And then it goes down in a and says, look, it is.
Well, we're using that fact. So we're using the fact that we know that f is at least differentiable at 1.
Yeah.
Because this is going to turn out to be the derivative of f at 1. That's what this is.
Yeah, I know. So they already did it for us. That's why I'm saying.
Yeah, I see.
In my head, it's already done.
Well, we need to come up with our continuous function real quick.
Okay.
Right? We need a continuous function that we put in here. And our continuous function is going to be this exact thing, 1 plus h. You're good with the fact that 1 plus h is a continuous function.
Yeah.
I mean, maybe I'll get crazy with it for this first one so that we can see exactly what's happening. So then, maybe I'll say, so this is all different ground. So maybe this is what we're evaluating, maybe we'll say g of h is equal to h plus 1. Okay?
Why are you creating g of h?
Just make it easier to write.
So that you can see explicitly how we're going to use a function inside of here. Good?
Yeah.
So, then what do we have? And maybe I'll even say, so that we can see it real crazy, like x naught equal to 1. Right?
Yeah.
Okay.
So, let's see how we can rewrite this limit. Well, so now we're taking the limit as h goes to 0 of f of g of h. Oh shoot, that's not going to work like I thought we. Because g of 1 is 2. So we want g of h to just be h. how exactly they intended us to do this problem without just thinking about the derivative like we would over there. They want us to use the fact that f of a continuous function minus f of a continuous function at a point as x approaches x naught, so h approaches 0 as g of x approaches
G of X naught.
so let me think again. G of x, or g of h, sorry. G of h, we were going to do 1 plus h. So as h goes to 0, or as g of h goes to 0, because now I want to think about this in terms of g of h.
H goes to 1.
As h goes to 0, g of h goes to 1, right? As h goes to 0, g of h goes to 1. So the limit as h goes to 0 is going to be the same as the limit as g of h goes to 1. And now we're going to have f of g of h. As g of h goes to 1, but what's 1 in terms of g? That's g of 0, right? Trying to do it exactly how we have it up here. So minus f of g of 0 over h is going to be g of h minus g of 0. You see that? Because g of 0 is just 1. And g of h is 1 plus h. So 1 plus h minus 1 is just h. So you good with the conversion of this to this?
Yeah.
Okay. So now, hopefully you can see it pretty explicitly right here. Very similar thing there. I just used a g instead of an h because we have the h already in the problem.
Yeah.
And this is equal to f prime of g of 0, which is equal to f prime of 1.
I see why they're saying that.
Okay, so that's how they're doing it. We view this as a continuous function,
Okay.
called it g of h. Rewrote everything in terms of g of h.
You have to prove it's continuous.
Here's my question.
It's polynomial. We know it's continuous.
I think my question is why? Like, why we had to get things in terms of g of h?
To use this theorem is saying if f is differentiable and h is continuous. So I need to rephrase this as a composition of a differentiable and a continuous function. I need it to be a continuous function being plugged into a differentiable function.
Okay.
Here's a continuous function.
Mm-hmm.
And then we know that f is differentiable.
Why?
It's
It
given.
says it.
Oh.
It's differentiable at x
X
naught.
naught.
In our case, 1. So in other words, I know that when I plug 1 into this function, I get a value. I know that this thing exists. F prime of anything else, I'm not sure. But I know that it works for 1, which is what it came out to. So I view the inside as a continuous function, rewrite everything in terms of that continuous function, and then, choosing that theorem.
That's where I would have got this at.
Right, rewriting it in terms of the continuous function. That was weird for a second.
Makes sense though? Think we could do the rest?
Okay? Good?
Mm-hmm.
One more thing. Wayne,
Go ahead.
sorry, your minus f of 1, how, like, what was your logic in putting that into minus?
I need 1 to be g of h. G of what gives me 1? 0. G of 0 gives me 1. So, what's right here? This was my g of h.
Yeah,
Now, what do I have to plug in for h?
2, 4, and
oh,
7.
okay.
0, the thing that h is
1,
approaching.
2, 4, 5, and 7.
Okay.
Good?
Yeah.
Okay. So let's continue then with derivatives of inverse functions.
You said 1, 2, 5, and 7.
1, 2, 4, 5, 7.
1, 2, 4, 5, 7.
You guys are terrible at counting.
I think it was you. You made us count like
Following our teacher's example on the syllabus.
No, I just meant you're terrible at counting in general.
and we meant you can't even count with the syllabus.
Like, if you have 10 people that randomly sit down on a bench, and only two of them are named Jack and Jill, what's the odds that Jack sits next to Jill?
And 2 of them are named Jack and Jill.
2 and only 2 are named Jack and Jill. 10 of them randomly sit on a bench. What's the odds that Jack sits next to Jill? A simple counting problem. Right, James?
20% chance.
That's correct. How'd you get that?
How did you get that?
A human being has 10% chance of sitting next to another human being if there's 10.
Okay, what if there were 11? Maybe you just happened to guess the right answer.
I don't know how you went about solving it.
Yeah, math simple enough you should be able to do it in math.
11. 20%?
Oh. It can't be 20% with 11 if it was 20% with 10.
Yeah,
Because think about if there were only 2 people. 100%. Okay, so 3 people's less than 100. It's going down the more you add. You can't have the same probability for 10 and 11, so your
well, I was just thinking
sanity check should be
a
straight.
last person.
No, you can't be the same.
a next person. Well, my thought was
Well, your thought was wrong.
11 divided by 10%. So like 18% roughly.
Well, now you're just randomly picking.
No, I'm not.
How are you catching that?
11 divided by 100.
11 divided by 100?
It's like 9 point something million times 2. 18%.
Well, the answer is 2 over
18%.
11. They're going to come out roughly the same, but you're calculating a weird way. You're not counting.
I'm calculating in the same way you're calculating.
No, you're not.
Okay, I'm taking.
Here's what I'm doing.
I'm taking 11 divided by 100 times 2.
Here's what I'm doing. Which is how you count it.
And I'm doing 11.
You're doing.
No. 11 divided by 100 times 2.
Oh, because you're trying to get a.
Because that's one person.
You're doing 11 divided by 100 times 2. Okay, so 22 divided by 100.
No. Yeah, 22 divided by 100.
It's not the same thing as 2 11s.
That's close.
22 divided by 100 is now bigger than 20%.
No, no. Okay, then. 9. I didn't.
Right, now you're just randomly throwing out numbers.
No, I
Probably
did something in my head. Because I got 18%, just like you.
Well, that's not exactly 18.
I know, I
You
said
could've guessed.
roughly
It
18.
needs to go down a little bit, knock off 2%.
No, that's not
Now,
what-
what will give you knocking down?
I promise you that's not what I did. The first time I did 1 divided by 100, or 1 divided by 10. Oh, I did 2 over 11. I'm pretty sure I did 1 over 11 times 2. That's what I did. That's actually what I did. I don't believe you.
Alright. So let's get our intuition real quick for the derivative of an inverse function. Now our intuition for a derivative is the slope, right? So if I have some function plotted on here, and it looks something like that. Here's our x naught, and here's our corresponding y naught.
I hate inverses.
Then the slope of this thing is going to be our changes in y's over our changes in x's, right? Slope. Well, when you think about it as an inverse function, now this is the input and this is the output, then now your slope is your x's over your y's instead of your y's over your x's. So if the slope of if m prime at x naught was equal to m, then we expect f inverse prime, I'm not sure how to mark that, at y naught to equal 1 over n, intuitively. So let's make sure that the intuition makes sense, and then we'll go through the actual, well, we'll do some examples to see it happening, then we'll do the proof. If my changes in y's over my changes in x is equal to m, then my changes in x over my changes in y's is going to be 1 over n at the same point.
Yeah.
And there's two ways that we can think about this point. We can think about this point as x naught, f of x naught, right? Which is the same thing as y naught.
I want to think of it.
This is the same thing as y naught. And x naught is the same thing as f inverse of y naught. Right?
Yeah.
Why is x not f inverse of y not? Oh. What's it?
The inverse gives you the x's. F takes x's and gives you y's. F inverse takes y's and gives you x's. It undoes it.
Okay.
Make sense? So does the intuition make sense that this is what we're expecting?
Yeah.
Yeah, well, just because we know inverses. flip.
Well, just from kind of what I'm pictorially representing here. This is just establishing intuition. This isn't proving anything yet. We're just showing what our expectation is, and then when we go through doing it, we're going to get our expectation. Good? Okay, so let's actually do it with a couple examples, and then we'll prove it. So let's do a function that we know the derivative of real easy, and a point that we know real easy.
X squared.
X squared. So f of x is equal to x squared. So we already know f prime of x
It's 2x.
is equal to 2x. Now to do the inverse of this, we need to limit our domain. I'm not going to write that out, but remember, this only has, we typically define this from 0 to infinity. So we have f inverse, it's from 0 to infinity to r, by f inverse of x is equal to square root of x. Maybe we'll do y's here to help us keep clear. Right? If we include the negative numbers, then this thing's no longer a function.
Yeah.
Yeah.
But I'm confused about your square root.
Yeah, I'm just doing the inverse of this. What's f inverse?
I thought f.
What's f of 3?
9.
What's the square root of 9?
3.
Okay, I guess it's back where we started. This is the function that undoes this. For any y this spits out, this will give me back to my x. I mean, we could calculate it the way that you're used to calculating it.
No, it makes sense.
Do you know how to calculate an inverse function in general? So let's write out a random function and calculate its inverse. So let's say that
No, you just do 1 over.
f of x is equal to, no, it's not that simple. What should we do? X, should we do like 3x minus 7 maybe? So what's the inverse function of that?
Whatever.
How do you do it? Well, first off, the general
Oh, you flip your y.
formulas, yeah, you start rewrite it in terms of x and y, and then flip your x's and your y's. So you have x is equal to 3y minus 7. So here's where we're getting our inverse function. Now write it in terms of y. And now y is equal to 1/3 x minus 7. This is the inverse function of this. So f inverse of x equal to 1/3 x minus 7/3. If you want to write that way.
Okay.
Same exact thing we could have done over here. We had y equals x squared, swap them, we get x equals y squared, y is equal to plus or minus the square root of x, and then we ignore the negative cases, we get a function. Good? Okay, so that's our inverse function. And we're limiting the domain to positive numbers. Okay. So now so we know we need to do it at a point. So pick a point. We know f prime at,
1 is 2.
2.
let's pick a different number. Let's do 4. F prime at 4 is equal to 8. So we're guessing that f inverse prime at, at what? What are we going to plug in there?
4.
No.
8.
No.
Is it 2?
No.
No.
What's f of 4?
Oh,
It's 16.
16. So we're guessing that f prime at 16 is equal to 1/8.
Okay.
Good?
Yeah.
That's all we're guessing. Oh, because of our earlier, yeah.
Yeah, from our earlier intuition. When we calculate this, we're expecting this to come out 1/8.
Okay.
Or in general, we're expecting f inverse prime at x squared to equal 1 over 2x. That's what we're expecting in general. Good with that thinking? Okay. So let's calculate it and see if we get 1/8. So let's see. So we're doing this, so what do we have? So we're taking the limit as y approaches 16, right?
Yeah.
Of the square root of y minus the square root of 16 all over y minus 16.
That's the definition of a
Yeah.
derivative.
This is, yeah, the definition of the derivative of this thing, right? So we're just going to evaluate this and it better come out 1/8.
Inverse prime.
Otherwise we screwed up. Yeah, this is the derivative of this function at the point 16. Right?
What are we wanting it to equal?
Let's get rid of this. We expect it to come out 1/8.
Right.
We expect it to be the inverse, or the reciprocal of this. Good? Okay. So, let's see. We can't take the limit of this directly, because that's in the denominator. What are we going to do?
Times by difference of squares. So y plus 16.
Right. So we're going to multiply the top and bottom by square root of y plus square root of 16 over, that's going to give us the same problem, isn't it? Oh my goodness. Rewrite the bottom. Here we go. Rewrite the bottom as a difference. As factor the bottom. And the bottom is going to factor into square root of y minus square root of 16 and square root of y plus square root of 16. Follow the logic there?
Yeah, cancel out top and bottom.
Cancel out top and bottom, so we're left with the limit as y approaches 16 of 1 over the square root of y plus the square root of 16, which is equal to 1/8. Okay, so it worked as expected.
That actually
Cool.
worked.
I'm actually shocked.
Okay. What are you asking actually worked?
I always get held up on the polynomial thing.
I'm moving about the polynomial thing.
Trying to factor out y equals or
A difference of squares?
difference. I always get stuck on that.
You need a marker for me. A squared minus b squared. Right out the door. A plus b times a minus b. You need that memorized so bad, it hurts. You can't keep wondering what to do when you come across a difference of squares. That's like in trig, wondering what to do when you come across sine squared plus cosine squared.
One.
You need to just do that. You can't be having to look that up every time you come across or getting stuck in that. It's like the most basic tool you use over and over again. Difference of squares is the most basic tool you're going to use over and over again in derivatives. It's typically how you're going to get something you can take the limit of. They're always going to be set up, that goes to 0. That's always the case.
Good show, that worked.
Okay.
Okay, so how
Didn't
does that
seem
equal?
that simple.
Yeah, I don't know why, but I'm getting so stuck on the algebra.
What?
How does that
Plus the
equal?
square root of 16.
Four.
Oh, 4.
Plus the square root of 16.
Plus.
When you take a 4 and you add it to a 4, you get one more.
Depends on what 4 means.
20%.
Well, you know what 4 means, what you don't know is what plus means. You know 4 is the second containing 3, 2, 1, and 0. But what does it mean to add those two sets together? Or add that set to something? Okay.
Is this more fun to you than derivative or than discrete math? This crap seems like a ton of fun.
Depends. Discrete math, there's stuff we go into that I really enjoy and stuff that we go into that I don't enjoy as much. My favorite field of mathematics is topology.
Studying
Which is what the
the
study
floor of the ocean. That's what I thought topology was.
Topology at its most fundamental level, what you're studying is
Graphs.
No. Geez, how can I do this real simply? I keep trying to use examples that you don't know.
Seems like a complicated field.
A sameness. Okay, so a sameness that we're looking for in. Well, first off, one of the fundamental definitions that we make in topology is what it means for functions to be continuous. So you have sets, and then you start out by analyzing continuous functions from sets to sets. And the first sameness that you come across when two continuous functions are actually the same, we call them homeomorphic, if they're the same in some way. And we have a sameness relation, kind of like congruent is in geometry. Congruent doesn't necessarily mean equal, but it captures a sameness in some sense. These two shapes are somehow the same. So basic topology, you're analyzing the sameness of continuous functions. What we get to in calculus is a special case of topology. So what we're doing in calculus is we're analyzing the topology on the real, what we call the standard topology on the real numbers. looking at a special case of topology right now, even though you don't know what topology is. And what we mean by continuous function in calculus is a special case of what continuous means in topology. And functions being continuous is a very general thing, and we have a very specific what that means when you talk about the standard topology on real numbers. Here's what continuous is. It's a very special case. It's a hard topic to just get intuition for because it's very fundamental like that. And then one of the things you're interested in is one of the ways, okay, so the standard example is if you were to look at the surface of a donut and the surface of a coffee mug, those two things are topologically equivalent.
Like the surface area?
No. What I mean by that is there is some mapping that I could perform from a coffee mug to a donut that keeps points that are already close to each other still close to each other. So these types of topological morphings, all that has to be preserved is points close to each other are still points close to each other, and points not close to each other are still not close to each other. That allows you to do things like stretching and reshaping, but what you can't do is like close a hole. Because if I have a hole, like a coffee mug handle or a donut, then a point here is definitely not close to a point here, and there's no way for me to close that hole without making them close. If I can stretch the hole, the point here will still be next to the point here. I just stretch it and make it bigger. Those two points are still right next to each other. They're just stretched. Think about kind of an elastic.
But how's that mathematical at all?
That's
That
awesome.
seems very applicable. Like very much hands-on.
This is to help you get the intuition for it, but it's very low level. The same way that you got intuition for a limit by thinking about derivatives, when really it had a more low-level definition of what exactly we meant by a limit, convergence. And chances are, I don't know how your calculus class was, but you don't really get to convergence typically until calc 2. So you go through all calc 1,
We've already done
and then you
it.
come back. Right, it's where you have to start. Because convergence is how we define the limit, and then this is just a special limit.
So in my calculus class, they just said this is what a limit is.
They give you high-level intuition. They do a lot of pictorial arguments. They often say, you can see that as this happens, without it ever being precise what exactly you're talking about. So that's the same as you can see high-level type stuff, but no, topology, very low level. I haven't done a more abstract class in
So
topology.
it's not very applicable, like to the real world.
Depends on what you mean. So, general relativity talks about a mathematical object called a space-time, which is a special type of differential manifold, which is a special type of manifold, which is very much a topological object. And general relativity is very applicable. So. But that's combining, once you get to there, you have to get to combining geometry with topology, being the two together. That's what a manifold does.
Are you there yet?
Am I there yet? I don't understand the question.
Have you combined geometry with topology?
Yeah, I've studied manifolds. It's one of the things we study in topology, and it's very fascinating. So I love topology. It's definitely my favorite topic.
We haven't proved this yet.
Right. So now let's do, I don't know, do you need to see another example to help get your intuition for this?
Sure.
Should we do a more linear one? So let's do a linear looking one. So let's do f of x equals, let's just do what we did before, 3x minus 7 is what we did. Okay, so f of x equals this. We know that f prime of x is equal to what?
1/3 x
3x.
N over n minus 1. Or n.
Let's remember our derivative rules from last time. We're definitely going to have to make you guys do this on a test. We know that if f of x is equal to x to the n, f prime of x is equal to n times x to the n minus 1, right? Remember that one?
Okay.
What else did we have? We had that maybe that's kind of a verbose way to write it. Let's see a better way to write that. If we have x to the n prime, that's equal to n times x to the n minus 1. If you have f of x times g of x prime, that's equal to f of x g prime of x plus
G prime.
f prime of x g of x. The product rule, right?
Okay.
Are all these feeling kind of weird?
Mm-hmm.
Okay, maybe just gonna write out just doing tons of derivatives real quick. Just pick all sorts of random things and we're gonna start calculating their derivatives. And just see a bunch of examples to help you get comfortable with these. But the next one would be,
Don't we do addition?
You did one, no, you did 1 over g or something.
oh, we could have done addition, but that one's exactly what you expect. The derivative of f of x plus g of x prime is equal to f prime of x plus g prime of x.
You did the remember it was like 1 over g of x.
The derivative of 1 over g of x is equal to negative g prime of x over g of x squared. And then the quotient rule, if we have f of x over g of x prime, that was equal to
G
g of x f prime of x minus
G prime of x
f of x g prime of x over g of x squared. Okay, so these were all the things we proved last time. If you're uncomfortable with any of these things, you need to go rewatch the lecture, make sure you understand these things inside and out.
Don't we have to
And the
prove
more I
these?
think about it, I'm probably just going to put these flat out, prove it
Fine.
on your test. Because this is very, very basic. You need to understand these 5 things. And then we're going to do, the inverse one isn't as big of a deal, but when we do the chain rule, that one's another big deal, so I'll probably add the chain rule, so you'll probably be doing those 6 things.
And then show 10 from test.
I don't know. We'll see how this comes out. So let's just calculate a ton of derivatives just using these rules. So first off, you know how to calculate the derivative of anything like if I say x cubed, what's that equal to?
3x.
That's just using this rule. The derivative of x to the n is n times x to the n minus 1, one less. So this, whatever this number is, comes out in front, n times x to the n minus 1 now is 2. Right? What about if this were x to the negative 1? Let's make sure that you understand what that would look like. 1 over x, or x to the negative 1. How do we do the derivative of this? We're talking about the derivative of this. What's the derivative of this equal to? Negative 1 x to the negative 2. Good? All right. What about the derivative of x to the 0?
0.
0. Okay. So you know how to handle negative numbers, positive numbers. Let's do another one. What about if we were doing x to the 5/3? Derivative of that.
That's x to the 5 over x cubed.
Way overthinking.
5x
Yeah,
over
it's
3.
fine.
5/3 x to the 2/3.
Oh, really?
Yeah, remember that this
we
worked.
that just for
We
natural.
proved this for, we did for naturals, and then we did for negative integers, and then we did for rationals. So for any rational number I put here, this works.
And, I forgot about that.
Okay? So that's the first rule.
Okay.
Alright, let's see the second rule. Give me a function f of x.
3x plus 7.
3x plus 7. Give me a function g of x.
2x.
Huh?
Just 2x.
X squared. Good choice. Okay, so we got two functions. Now let's calculate the derivative of their product. So what's their product?
3x cubed plus 7x squared.
So f of x times g of x, we are calculating the derivative of the product. That's equal to the derivative of, I'm just going to multiply this by this. What do we get? 3x cubed plus 7x squared. Right? We're taking that derivative.
9x squared.
According to the sum rule, the derivative of the function, I can view this as the sum of the derivatives. So I can take the derivative independently. I can take the derivative of 3x cubed, take its derivative, plus the derivative of 7x squared, take its derivative. Now remember that the derivative is a type of limit, and you can pull constants out of limits.
Okay.
So this is the same thing as 3 times the derivative of x cubed plus 7 times the derivative of x squared. Alright? Which is equal to, what's my first term now? What's the derivative of x cubed?
It's 3x squared.
Times 3. It's 9x squared. And what's this one come out to?
That's 14x.
14x. Alright, nice and easy. So here's what we got, manually calculating it all by hand instead of just using the rule. Now let's just use the rule. So I'm going to do the exact same thing. I'm doing the derivative. I'm calculating the derivative of the product. I better get this thing, but this time I'm going to use a rule. Okay? So I'm going to do, it's equal to f of x times g prime of x plus f prime of x. What's f prime of x is 3. You see that?
What happened to the 7?
What's the derivative of 7?
It's constant, so it's 0. This one's looking right.
Maybe if I rewrite this as 7x to the 0, you can see it better. Okay? So you go with f prime of x is just 3,
Okay.
and then g of x. So I just flat out wrote down this. Simplify, what do we get? We have 3x times 2x is 6x squared. We have 7 times 2x is 14x. We have 3 times x squared is 3x squared, which is equal to 9x squared plus 14x.
Okay.
Same thing. So we didn't have to do all this work if we didn't want to. We could have just used a rule. Good? All right? Now let's do f of x over g of x. So the derivative of f of x over g of x. So we're doing oh boy.
X squared times
Well, I was going to write it out without using the rule, but it's going to get messy. Should we write it out without using the rule, or should we just use the rule and see how to use the rule?
Use the
Just
rule.
use the rule.
Because otherwise we're going to have to do the limit as x approaches x naught and value this whole thing. Okay, so we'll just use the rule and see what this goes out to. So this is equal to g of x times f prime of x minus f of x times g prime of x of x squared. Right? So that's going to give us 3x squared minus 6x squared minus 14x over x to the 4, which is going to give us negative 3x squared minus 14x all over x to the 4. Right?
Okay.
So that's its derivative. There's f prime of x. Or sorry, there's the derivative of this over this. So I say use the rules. Any question on any of those? So these are the rules that we're using over and over and over again. These rules never go away.
Okay.
Huh?
That was a big class. We pretty well those.
They're all really simple proofs.
Yeah, you should seriously do that. 'Cause that makes it super easy.
So, yeah, understanding those rules is a big deal. I won't make you do this for rationals, I'll only make you do it for naturals.
So our sequence, we minus the two sequences.
What?
Remember the sequences? We take a sequence and then you don't minus them.
You're going to have to remember that x to the n minus x naught to the n is equal to x minus x naught times x to the n minus 1 x naught plus
Right.
x to the n minus 2
X to
this is x naught to 0 times x naught to 1 plus blah, blah, blah. You are going to have to remember that rule to derive this one.
Right.
James, that rule that you hate so much, you need to just go and redirect that rule 1,000 times maybe. Just get it clear in your head because, my goodness, it's one of the most useful identities I can think of in algebra. Binomial expansion. Plus you saw that in discrete math.
Anything I'm gonna struggle with?
I remember Sophie telling us about how binomial expansions can be one of those things we use, and I believe her. Sorry. She wanted us to do the whole triangle. What is it called?
Pascal's triangle.
Yeah.
Knowing the triangle just helps you with tricks, but we learned it the best way to learn it because you can calculate it so much faster than you're looking for.
Discrete math.
Yeah, we learned it in terms of counting. And so you get very comfortable with choose notation because you have great intuition for what choose means, as well as a definition, or as well as an equation to calculate it. So, binomial theorem is a significant part of one of the chapters that we go over in discrete math.
I remember Mr. Michael going over this in geometry.
A derivative.
No, binomial expansion, and I read blew up me.
Yeah, I've debated whether or not proving it for you guys, but it takes a good 20 minutes to a half hour to go through the proof. Okay, so we were talking about inverse functions, and we just did an example of an inverse, right? And we showed it came out as expected. So we get to continue, or we need to see another example with the inverse function coming out to 1 over the slope.
Another example.
Do another one? Okay. So f of x equals
1/3 to the x squared.
1/3 x squared. All right. F of x equals 1/3 x squared, I guess. So, what's our inverse function?
Square root of 1 second. So you replace it with y times 3x square root of 3x.
3, yeah.
Square root of 3. Oh, f inverse of y, right? To try and follow what the author's doing. That's the square root of maybe we'll separate the coefficient. Square root of 3 times the square root of y is the inverse function. Good? Okay, so there's our inverse function. Pick a point.
Isn't it square root of y squared? So it should just be y.
So we'll manually calculate it then. Y is equal to 1/3 x squared. Or in other words, x is equal to 1/3 y squared. So y squared is equal to 3x, so y is equal to plus or minus the square root of 3x. Is f inverse.
That's what I said. So,
You just separated them.
Oh, is that all you were saying?
yeah.
The fact that I separated them?
Well, I was just like, why did you do that?
So I have the coefficient and the variable.
Oh, okay.
Because good practice. Anyways, pick a point.
1.
1. Okay. So what is, well, first off, what's f prime of x equal to?
Square root of 3 times square root of y.
It is.
F prime.
Oh, sorry.
2/3 x.
2/3 x. Oops. 2/3 x. So f prime at 1 is equal to 2/3. So what do we expect? What happens when I plug 1 in here?
Hey, it's 1/3.
1/3. So I expect f inverse prime at 1/3 to equal 3 halves.
Just 3.
Halves.
No.
Oh, yeah.
The reciprocal of this.
This is so much flipping and flopping, dude. I get so confused. Okay.
If f prime at x naught equals 2/3, then f inverse of y, f inverse prime of y naught is equal to 3 halves. Right? X naught is equal to 1, y naught is equal to 1/3.
Yeah.
So if f prime of x naught is equal to 2/3, then f inverse prime of y naught is equal to the reciprocal of that, 3 halves. Good? Now let's see if it comes out as expected, which obviously it will. So we're taking the derivative of this thing. What is the derivative of this thing?
0.
So we've got the limit as y goes to y naught, but in this case we're doing
1. 1/3.
1/3. So we're taking the derivative as y goes to 1/3 of, maybe I'll keep them combined for the sake of writing, the square root of 3y minus the square root of 3 times 1/3
1.
all over y minus y naught. Right?
Difference of squares.
Yeah, we need to view this as a difference of squares. Well, before I do that,
Do you want to take out the freeze in the top?
yeah, I'm going to pull the square root of 3 out of the whole thing. Square root of 3 is a constant. I can factor it out of the whole thing. So you were tempted to make this a 1. We don't want to make this a 1. Because when we look at this as a difference of squares, it's going to have a square root of 1/3 in it. So I'm going to factor the square root of 3 out here. So I got square root of 3 times the limit as y approaches 1/3 of the square root of y minus the square root of 1/3 over y minus 1/3. Any confusion about that? Does that make sense? Okay, just pulling out constant. Okay, now once again, this factors into the square root of y minus the square root of 1/3 and the square root of y plus the square root of 1/3. Maybe I'm going to skip straight to this is equal to
square root of y
the
plus
limit as y approaches 1/3 of 1 take our limit. So we get the square root of 3 times 1 over the square root of 1/3 plus the square root of 1/3. Or 2 square roots of 1/3. Good?
Mm-hmm.
Times top and bottom by the square root of 1/3.
You get 3 over.
Maybe I'll be real verbose. Square root of 3
over
times the
2.
square root of 1/3.
Oh,
All
2.
over 2 over 3. Right? And then obviously this is 1. So we get 1 over 2 over 3, which is 3/2. Oh, wow. Good shot at coming. Okay?
Mm-hmm.
Alright, so we've seen it in action a couple times now, it's proven. It's almost 11. Holy crap. Barely getting started.
No, get started. All this inverse, bro. New material, bro.
Now, we covered that last time.
We did?
We're now where we were last time. Yeah, we did. Alright. So, if f from I to R is strictly monotone, I'll explain why that matters in a second. And continuous.
When we see I to R, should we think that I is in a closed interval?
And differentiable at x naught where f prime of x naught is not equal to 0. Then f inverse from f of I to R is differentiable at y naught equal to f of x naught and f inverse prime of y naught is equal to 1 over f prime of x naught. Okay. So here's what we're proving, but let's make sense of why they're giving us all the conditions that they're giving us. Get rid of all this stuff. So, first off, why are they making f from I to R strictly monotone? The reason that they're doing that is that the inverse is a function.
Oh yeah, so it's not, so it's 1 to 1.
So it's 1 to 1, in other words. It's guaranteed to be 1 to 1.
If it's mono.
Stupid.
If f is strictly monotone, then it's 1 to 1. Right? And then a continuous function and differentiable at a particular point where its derivative isn't 0 because we're going to say it's this in the end. So we don't want to divide by 0. That's why we're throwing on that condition. So then the inverse function is differentiable and it is what we've been saying this whole time. So you understand why we have all the conditions that we have written up there?
Yes.
Not blues,
Well, maybe I'll ask this question later.
Go ahead and ask it.
In discrete math, did they explain why you can't divide by 0? Why it's undefined?
Why it's undefined?
Yeah, what does this mean? Because we've been throwing that at our whole lexicon. Divide by 0. It's undefined. Well, what is the number 0 in discrete math? That percent?
Well, I don't remember if we came across that in discrete math, but we definitely did it in geometry. Early in geometry to demonstrate why why division is undefined. When you do 0, and it's because of how you define division. So what did we, in fact, we probably did in this class.
We did. This divides.
What does it mean to say that A is equal to B over C? B divided by C when we were defining divides.
C times A equals B.
Right. We define that to mean that C times A equals B. A is the unique number that makes this true. If C is equal to 0,
You get rid of A.
what number makes that true? What's the one and only one number that makes that true?
B. What do you mean?
There isn't one, unless B is 0. And then if B is 0, how many are there?
What?
Infinite.
Wait.
There's either no numbers or there's infinite numbers. Now, understand what we mean by a definition. A definition means this. It has to be a unique number to be what we call well-defined. If I say, what's the definition of a word, and you look it up in the dictionary and there's nothing there, it's not a defined word. If I say, look up the word in the dictionary, and you open it up and it says this word is every word in the dictionary, that's not a definition. You can't have it be every number and have it be defined. You can't have it be no number and have it be defined. It needs to be one and only one number. It's not one and only one number, so it's not defined.
Stupid. 0 is retarded.
0, wonderful.
It ruins everything.
Makes everything work. And so you have similar problems, although this one isn't used as much for 0 to the power 0. You can break things if you use this, defined to be 1. But a lot of places it's useful to put 1 in for that, and so if you type this into a calculator, some calculators will actually spit out a 1. Anyway, so that's what it means to not be well defined. It means there isn't a definition.
Because it has so many. Makes sense.
Because how do you define it? Do you define it to mean there isn't a number, or do you define it to be every number? Makes sense. Okay, so this proof. Okay. So let x be f inverse of y. That's the shorthand notation that we're going to use, which you're already comfortable with. Right?
Yeah.
This is just a plugin I'm going to be using as we do substitutions throughout the scene. So 2. So what are we looking for? We are looking for the limit as, I assume we're going to have to do it in terms of x approaches x naught. Let's see how they sort it out. Define that so that that's equal to that. Yeah, that's fine. Since the inverse of that is continuous. Oh, that's how we're thinking about doing this. Let's kind of jumping around. Let's see how I want to say this. I'll just do my own way. We'll see what we get. So we're taking the derivative of this. So that's going to be the limit as y approaches y naught of f inverse, f inverse of y minus f inverse of y naught over y minus y naught, right? And now, to get the same, because look at what we're doing here. We're saying that the derivative of this thing, and we're describing it in terms of our function that we start out with. We're not just defining it in terms of our inverse function. We're defining it in terms of our original function. So I want to convert my y's and my f's inverses to x's and f of x's. Do you understand what I'm saying? Well, maybe just write it and then we'll re-talk about it. So we're looking at the limit as y approaches y naught of f inverse of y then is just x minus x naught over f of x minus f of x naught.
Oh, that's tricky.
With me?
Yeah.
Okay. Maybe I'll just write it. I think you'll get it. So this is equal to the limit as y approaches y naught of 1 over f of x minus f of x naught over x minus x naught.
Yeah.
You good with that?
Oh, yeah.
Okay. Now, obviously, the only thing we need to change is we need this to be the limit as x approaches x naught. Okay? And we are going to use the fact that
That it's continuous.
f is continuous.
Just like
Right.
we did it before. Makes sense why that problem was in our book.
Yeah, it's literally setting you up for this. So same exact thinking as before. Since f is continuous, then the limit as x approaches x naught is the same as the limit as y approaches y naught.
Right.
Right? Wait, we got to be a little bit careful about this. Because this isn't true in general just because it's continuous. It's because it's continuous and it's monotonically increasing. And it's strictly monotone. So remember, strictly monotone means it's either always increasing or decreasing. So there's only one point in the function where it takes on the value y naught. So the only way that y approaches y naught then is if x approaches x naught. See, if you had some other function,
Yeah.
here's y naught. Well, y can approach y naught here, here, and here. It's not just as x approaches x naught. Here's x naught. It's not just when x goes to x naught that you get y naught. That's not always the case. It is the case when you have a strictly monotone function.
So in our proof.
So
we're
because
gonna
it's
have to
strictly,
say-
in our proof we were going the other way. We were using the fact that x approaches x naught to imply y approaches y naught. This one we're doing it backwards. We're using the fact that y approaches y naught to say that x has to approach
Still
x
in
naught.
that proof, you're gonna have to say it's strictly monotone.
In the previous proof we did?
Yeah.
No. So, in general, if it's continuous, if f is continuous, then the fact that the limit as, how can I say this? Then we know that this is true. The limit as x approaches x naught of f of x is equal to f of x naught.
Right.
We know that as x approaches x naught, f of x approaches f of x naught. So we know that as x approaches x naught, y approaches y naught. This we're doing it different. We need to say that as y approaches y naught, x approaches x naught. It's backwards.
Oh yeah. I see.
You see
That
the
makes
difference?
sense.
So over here, look, as x approaches x naught, y does approach y naught. That's true.
Well, there's
But as y approaches y naught, it is not true that x approaches x naught. Y approaches y naught right here. This isn't x naught. Y approaches y naught right here. This isn't x naught. Y approaches y naught right here. This isn't x naught. Y approaches y naught here, which happens to be x naught. So it's not true that just because it's continuous, that this limit means this is the same as the limit as x approaches x naught. That happens to be the case for a strictly monotone function. So we're using the fact that it's strictly monotone and the fact that it's continuous
right there. Right.
to say, okay, now this is the same thing as the limit as x approaches x naught of 1 over f of x minus f of x naught over x minus x naught, which is 1 over f prime of x naught, which is what we're trying to prove.
Wait, with the limit, you can take the limit of a quotient is just the. You can just factor that in.
The limit of a quotient is the quotient of the limits. So we could split this up into the limit of 1 and the limit of this thing, and we know what the limit of this thing is. It's that. We know what the limit of 1 is. It's that.
Okay, I have another question.
Go ahead.
All these proofs we've been using I to the real. Why has it stopped being real to the real?
Oh. I is an interval. I didn't say that here.
It's a
Sorry, I
closed
thought it was
interval,
implied.
right?
Huh?
It's a closed interval.
No, it's just an interval.
Why does it need to be
Yeah,
an
why
interval?
does it need to be in?
We've always seen R. I'm just wondering, like,
The function might not be defined on all the real numbers. Maybe you're dealing with a function that's only as long as your function is defined on an interval, this works. The real numbers are an interval. But we're interested in functions that aren't always defined on all the real numbers.
oh, and an interval has all real numbers. Meaning, in the interval, it has every number.
Right, you know what an interval is.
Right. That's,
Yeah.
okay, it makes sense.
Right. So we're talking about a function from an interval.
Intervals only deal with real numbers.
Every time we're talking about an interval, we're talking about interval real numbers.
Right.
Any other questions? Sorry, I should have specified that. I thought you all understood now, but I never time to put an I there.
The book's just been written, so.
So I is a neighborhood of x naught if we're being real explicit.
Right. Does the neighborhood have to have something?
Which I think actually makes this an open interval. In terms of topology, it would be an open interval, so I bet it's an open interval for a neighborhood. I don't remember the exact definition of neighborhood, but based off of topology, I'm pretty sure that it's an open interval. I don't remember where we defined it. Anyways, so there's a function. Now this function has a small corollary. And the corollary is that the derivative of this at x is equal to 1 over f prime of f inverse at x. Now, why would we want to think about it? Because we said it was defined this way, right? But how can I make this make more sense to you?
It looks like it's that notation because of the y's, right?
It's a different notation. It's a different way of explaining it. It's like, yeah, we want the main focus to be we want to think about the inverse function in terms of x now. If you want to think about, if you want to think about the inverse function in terms of x, then you just use this. It's doing the exact same thing that we did over here. But in this one, we were just thinking about the inverse function in terms of y. Do we need to see an example of how these are the same real quick, or does it make sense when I
No,
say it?
it makes sense. But
Okay, so hopefully we can get to, finally, the chain rule. Oh, they did an example real quick seeing this in action. So, we'll do their example real quick. So they're saying g of x is equal to x to the 1 over n. Is that all we're doing? We already know how to do that. Oh, maybe they just want to do it the inverse function way and see that gives us the same thing. Okay, so we already know how to calculate the derivative of this. If g of x equals x to the power of 1 over n, what's g prime of x?
1 over n.
It's 1 over n times x to the 1 over n minus 1, right? So we know how to do that. They're saying, let's think about this in terms of an inverse function and see that this idea works.
Okay.
Okay? So the inverse function of this, g inverse of, maybe I'll do y here so that we remember what it is what? Y to the n.
Oh yeah, because you bring it on the bottom.
It's just whatever undoes this.
Right.
This takes the nth root, so this takes the nth power.
Okay.
Right?
Mm-hmm.
Okay. So, now let's calculate the derivative of this thing.
And y, n minus 1.
Well, of an inverse function, right? So we're going to use, how do we calculate the derivative of an inverse function? We're going to do it in terms of x. So what's that going to come back to?
1 over n y.
1 over that.
Oh, in terms of x?
Well, yeah, is this going to come out weird? Let's just do the x. That way it comes out with some variables. Alright, so g inverse of x then is x to the n. So now, using this, what do we get? What's the derivative of this now?
N to the x minus 1.
I think I'm confusing you with how I have the inverse written here. This is the inverse of what we were finding the derivative of. This is the inverse of what we were finding the derivative of. So in other words, if I view this one as g of x, now what we started with was g inverse.
Okay.
Right? But since this was g of x, now this is g inverse. In other words, this is the thing that's going to be in the denominator here.
Yeah.
You see that? The inverse of whatever we start with. This is the inverse of whatever we started with. Okay, so this is going to be 1 over the derivative of this thing,
It's going to be 1
n
over.
times x to the n minus 1, right?
Over.
Sorry, let's just think about something. Okay, and then what does this equal? This is equal to 1 over n, we can still do that, factor that out, times. Remember, if you want to bring it to the numerator, you make the exponents, you multiply by a negative. So that's x to the,
Negative n plus 1.
what am I missing? Doing something wrong. What the heck? Doing something obviously wrong here.
This one goes for x positive.
Oh, what am I doing? I didn't switch. I need to use this because I want to keep it in terms of. Sorry. Okay. Here is g of x. Let's restart. Get rid of all this other stuff. And let's just do it in terms of that. So, we want to figure out what. Well, g of x is equal to, what did they say? X to the 1 over n is what we're looking for. So, this is the inverse to the function. Maybe we'll do f of it. F of x to the n.
Negative 1. Or negative n.
No, this is the inverse of this.
Ah.
Right?
Mm-hmm.
So, if we want to calculate the derivative of the inverse, which is what g is, here's how we do it. So, the derivative of g prime of x, the inverse, its derivative is equal to 1 over f prime, is n times x to the n minus 1, times the inverse of f prime, which was g. Okay, there we go. That's what we meant to do. Now everything makes sense. You follow that?
A little bit.
So notice g of x, the way we have it set up here, is also f inverse of x. Right?
Okay.
Here's f of x, here's f inverse of x. We want to calculate the derivative of f inverse of x.
Okay.
And we're using this equation so we can keep everything in terms of x. We are viewing our inverse function now in terms of x. Instead of doing what we had to do over there, going between x's and y's. We had, over here, we had our initial function in terms of x and our inverse function in terms of y. And you can think about it that way and do it that way if you want. But here's a shortcut if you want to think about your
Keeping it in x inverse.
keeping your f inverse in terms of x. So here's our f inverse in terms of x, and here's its inverse function. Right? So we intentionally set it up so the function we started out with was the inverse of f.
Okay.
So this and this are the same. You see that?
Mm-hmm.
Okay, and that's 1 over, and now we can think about these f's exactly how we want to think about them. F prime of this. Dude, I need to plug that in. You guys let me do all sorts of stuff. Okay, let's start with this piece then. What is f prime of this? What does f prime equal in general? So here's f, what's f prime of x? N times x to the n minus 1, right?
Yeah.
Okay, so now what's f prime of f inverse of x?
I thought f inverse of x is g of x. F inverse of x is g of x.
Right, same thing, but I'm just doing it in terms of our formula.
It's nx to the 1 over
Alright,
n.
way over. I've
It-
confused you guys way too much. Okay, restart. Restart from the beginning. Here's our formula, right?
Mm-hmm.
Here I have a g, I don't have an f. Screw it, I don't want to deal with g, I want to only deal with x. So to help me keep my thinking straight, to use a formula, right? I'm going to rewrite f inverse of x is equal to x to the 1 over n.
X to the n.
No.
Oh, right.
And
Okay, now ignore the g from here on out. F of xn is equal to x to the n. Let's see, I'm also going to need f prime of x. What's that? That's equal to n times x to the n minus 1. And I'm going to need f prime now of f of x. Or f inverse of x, right?
Yeah, you don't need f prime of x at all.
Well, I'm going to use this to help me think about this. So what's that equal to? That's equal to n times
X.
f inverse of x to the n minus 1.
to the n minus
That just
1.
got me there.
Yeah, you just gotta, you're plugging in the x.
What do you do with a function? You plug in the x.
Okay.
Look,
Your x
if I
is
say
x
f of
over
x
n.
is equal to 2x plus 7, what is f of SpongeBob?
Two SpongeBob plus
2 SpongeBob plus 7. If I say f prime of x is equal to n times x to the n minus 1, what is f prime of SpongeBob?
Oh, yeah, okay.
That is equal to n SpongeBob's to the n minus 1. SpongeBob! Alright. Good with all that?
Okay, I totally see it.
Okay. Now we know what f inverse of x is, so I'm going to rewrite this one more time. That's equal to n times
X.
f inverse of x is x to the 1 over n. Good with that? Multiply the exponent, that's n times x to the n minus 1 over n. Good with that?
Yeah.
Which is equal to, I'm going to split this into two factors. That's n times x to the n over n is 1 minus 1 over n.
Yeah, okay.
Okay, now use our formula. Right?
Yeah.
Now use our exponent rules.
what was also.
When we take that to the top,
Yeah.
you make the exponents negative. So, that's exactly what we expect it to be. We already know that g prime of x, right out the door, we know that g prime of x is equal to 1 over n times x to the 1 over n minus 1.
Oh,
Okay,
right.
exactly what we expected. Showing you how to use a formula.
Okay. So this is just saying, seems like that was a lot easier.
Yeah, in that case it was, because this inverse was a real easy function that we already had to work with. But if your inverse was something that you didn't right out the door know how to work with, it might be a lot harder. Maybe your inverse has. Our inverse happened to just be in terms of an exponent, and that was nice. But what if we were dealing with something like trig functions, where the inverse of sine is arc sine? What?
Close. Or,
The inverse of sine is arc sine.
I thought it was cosine. I thought their inverses would be cosine.
No!
Oh, there.
Cosine takes an angle, gives you the x coordinate. Sine takes an angle, gives you the y coordinate. Inverse, or arc sine, takes a y coordinate and gives you the angle.
Right, yeah.
Okay. Cosine does not spit out angles.
Okay. Oh, wait. The derivative of cosine is sine.
Yeah,
Yes. Yeah.
but
That's what I was saying.
Yeah,
have
that's
intuition
right.
for what an inverse
I
is.
get that. I get that.
Sine goes from angles to y coordinates.
Arc sine.
Arc sine goes from y coordinates to angles. Okay. So yeah, it happened to be easier to do it a particular way, which is why the author chose this example, so you can verify, yep, it works. I'm guessing that's why he chose this example. Sorry, a little bit messy in the beginning, didn't mean to confuse you guys so much. Okay, now we get to get to the chain rule.
Why are you so excited about the chain rule?
This is the last rule.
Is it unique?
The chain rule, it's so useful, and a lot of what we do can be reviewed in terms of the chain rule. So to get the chain rule, I'm going to start out with something we're going to have to use in the proof that it seems confusing at first, but it's going to make perfect sense why we do it. It's just to avoid a dividing by zero. Maybe, I don't know, is it better to show it to you first and then do the proof, or do the proof and then handle it as it comes?
Tell us.
Maybe we'll do the proof and just handle it as it
Yeah.
comes. Okay, so if we have functions such that you can compose them and still continuous and all that, well, maybe I'll write it all out. Well, not all of it, some of it. I is the neighborhood of x naught. So we have f from I to r. If f from I to r is differentiable at x naught, and g from f of I to r is differentiable at f of x naught, then g composed with f of x naught is differentiable. Or rather, this function is differentiable at x naught. Sorry. You understand the proof? Ever tried to prove? So f is a function from I to r, and g maps from the image of f to r. In other words, I can compose these two functions together and still get a function and everything's fine. So I know that this is differentiable at x naught. So let's get our picture. This is really from J, and then we specify that f of I is a subset of J. So j and then r. So f maps I to f of I, which is a subset of j. And then g maps j to the real numbers, who cares?
The subset J or just J?
J. It just also maps those numbers. So the numbers you start with here end up here. Okay. So and f is differentiable at x naught. So f takes x naught and maps it over here to f of x naught. And it's differentiable and how it does that. And g is differentiable at that point as well. So g being differentiable at f of x naught is the same as f being differentiable at x naught. We plug x naught into f, and we're guaranteed we get a derivative there. We plug f of x naught into g, we're guaranteed we get a derivative there.
Okay.
Make sense? So that's what we got so far. F from I to r is differentiable at x naught. G from j, which is a superset of f of I. So g from j to r is differentiable at f of x naught. If that's the case, then our function, our composition of these two functions, is differentiable at x naught.
Mm-hmm.
That's what we're proving. Good? Okay. Why were you shut? Okay. Okay. So for the sake of notation, we're going to let y naught equal f of x naught. And y equal f of x. And notice, the trick that we're going to do is we're going to say, notice f of x, is that on top or do we put the y's on top? Yeah. F of x minus f of x naught over y minus y naught is equal to 1.
Okay, well.
Yeah,
Wait,
what?
how come you are replacing the numerator with y's?
The denominator,
The numerator.
we haven't started our limit yet. I'm just saying, I'm going to define f of x naught to be y naught, and f of x in general to be y. Then notice that this is the case.
Oh, yeah, okay.
0 over 0. What?
It's not 0, because remember, oh, sorry. This is true as long as x doesn't equal x naught. Notice that when x is not equal to x naught.
Okay.
Good?
Mm-hmm.
Okay, so now it's to our limit. So, we're doing the limit as x approaches x naught of, let's see, g composed with f of x minus g composed with f of x naught over x minus x naught. That's what we're evaluating, right?
What?
1 second, why?
Oh, in the end, we're trying to prove that this is equal to, let's see, what is it? It's going to be g prime of f of x times f of x prime. So we're proving that this function is differentiable at x naught. So this limit exists, and furthermore, this limit is going to turn out to be this thing.
Okay.
function.
I don't know where you got that from. How did you know that's what we wanted?
It's in the book.
It's what well, I know the chain rule, but here's what we're doing. We're proving that if you have two differentiable functions,
Mm-hmm.
their composition is also differentiable.
Okay.
Furthermore, it's going to be this.
So it just says it's gonna be.
Yeah, it's the same way we did the product rule. We said we're going to prove that the derivative of the product of two functions is the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Mm-hmm.
Okay, same thing. So I'm going to prove that this is this.
Okay.
Okay? Alright. So this is equal to the limit as x approaches x naught. Now remember, in our limit as x approaches x naught, x is never actually equal to x naught.
Mm-hmm.
So this value is 1.
Mm-hmm.
So I'm going to multiply by that 1. And I'm also going to rewrite these. I'll just show you. I think you'll be fine with it. G of f of x minus g of f of x naught over y minus y naught times f of x minus x naught over x minus x naught. Okay, so I'm multiplying top and bottom by this. Well, let's take it one at a time. I've rewrote this term like this and this term like this. No problem with that, right?
Yeah.
Yeah.
Okay. Now I'm multiplying by this, top and bottom,
Okay.
which is 1. So that ends up there, that ends up there, and then I move this one over here.
I don't
Okay.
know why that would happen.
Well, it's just a different way of writing it. I can write 2/3 times 3/4 as 2/4 times 3/3.
Okay.
Right? It's still just a product at the bottom. I still just have this times this.
Okay.
Good with everything I've done so far? Now, something in there stands out.
Not getting it.
Huh?
I'm not getting it.
That bottom, or that second,
What aren't you getting? Are you saying that there was an algebra step that you're not good with?
What stands out cancels out.
no.
Well,
I
no.
don't wanna
I'm going to
cancel
do
out.
one more thing that will tie this whole thing together nicely.
Why did you get your x minus x naught in all these?
It's.
It starts out right here.
there. And then you just put it on.
The y minus y naught comes from the fact that I multiply top and bottom by y minus y naught, or 1.
Okay.
He put,
Oh, you multiplied. You multiplied in number 3, the first one, by number 2.
yes,
Okay, makes sense. I was like,
You multiplied by
I don't know how you
1.
factored that, right?
Why aren't you changing those fx and fx? No. To-
Well, now look at what we have.
you have.
We have the limit as x approaches x naught of this thing, and we know g is continuous, right? Because it's differentiable. Sorry, f is continuous, so it's differentiable. So as x approaches x naught, y approaches y naught.
Mm-hmm.
So I'm going to split this up into two limits. See if you can follow this.
Yeah. Which equals,
You follow that?
Mm-hmm.
Okay, now I'm going to overlook a detail that we're going to come back to and just evaluate the scene. So, cheating for a second here, so that we can follow our train of thought, and then we'll come back and explain. So then what is this? This is the derivative of g at y prime, or at y naught, right?
yeah.
That's exactly what this is. So this is g prime of y naught times what's this? This is f prime of x naught. One more time, that's g prime of f of x naught times f prime of x naught, which is what we were trying to prove.
Okay.
The detail we overlooked,
Is y versus y naught.
y minus y naught could be 0. Uh-oh. How do we handle that?
Oh, y equals f of
X can't equal. Oh wait.
So the way that we handle this is we introduce a new function, h of x, that handles a specific 0 case. So, or h of y, since we have it written in terms of y. So we're going to define h of y is equal to g of y minus g of y naught over y minus y naught. Oops. When, this, when y is not equal to y naught, and we're going to define it to be g prime of y naught when y is equal to y naught. Now remember, g is differentiable, so g prime of y naught is defined. Right?
Mm-hmm.
So this is a number, we're good. And then up here, we're never dividing by 0. We're good, right?
Okay.
Okay. And then so, I'm going to start at this step again and not do what I did before. Well, it still gives us the same thing. Maybe you can see it. So, rewrite this now. We're doing the limit as y approaches y naught of h of y times, we'll just evaluate this limit since we already know what this limit is, f prime of x naught. Good?
Mm-hmm.
Okay, now the limit as y approaches h of y, we have two cases. We have the case
Where y is not equal to y naught, in which the top one works out.
yeah, how can I say this better? If y is never equal to y naught, then we're just evaluating this, which comes out to g prime of y naught. And if it is, we evaluate this, which comes out to g prime of y naught. In either case, it comes out to g prime of y naught. It's not a very important detail, but it is a detail that you do have to mention because as x approaches x naught, y may take on the value of y naught. And so you could divide by 0 here. But we just define this to be a function, and we manually stick in that value for what it is, 0. You break it, just plug in whatever that value is, because we know that's what this is going to evaluate to anyways.
Oh, okay.
So in other words, this thing, when you look at this thing, if you were to look at a picture of it, it has a hole. It looks like this. And then we made h of y, we filled in the hole with whatever this was already approaching and whatever this was already approaching. Make sense? Okay. So that's what that side note is. You can read through more explanation of that if you want. But in short, there's the chain rule. And now, I assume he's going to have examples. derivative of x to any rational number. Maybe we didn't show that. So that looks like what he's doing right now. Go back to the last section. Oh, we just proved it was differentiable. We didn't say what the derivative was. That's what we did. Okay. Anyways, moving on with this example. So now he wants to do the proof. If R is a rational number, f of x is equal to x to the r, then f from 0 to infinity to r is differentiable, and f prime of x is equal to r x to the r minus 1. I think that's what we got. For x greater than 0. Okay, yeah, that's true. Alright, so let's do this using the chain rule now. 1. So r is a rational number. What does it mean for it to be rational? Since r is in Q, there exists n in N and m in Z such that r is equal to n over m. If it's a rational function, it can be expressed as a quotient of two integers. Furthermore, we can make the positive integer always positive if we want.
Okay, wait, so what is this proving?
We're proving that the derivative of x to the r, where r is a rational number, is r times x to the r minus 1.
I thought we already did this.
I thought we did too.
We did.
I'm pretty sure,
I think you confused
No,
it
I don't
and
think you've
decided
done
to prove it
rationals.
this way.
I thought you just did naturals and integers.
I think he was confused on the problem, and so he just did it as at the very beginning.
Yeah.
It does seem.
You
But
might have just thought we
the
already
n
learned
over
it.
m.
Well, n over n.
Prove that if you have two polynomials that are differentiable, they're quotient. We proved rational functions are polynomial. And this is just a special case of a rational function. But we didn't prove it's this exact thing.
Well, my guess is that we're gonna have to use the composition functions to prove it.
Yeah, but we could have also proved it directly because it feels vaguely like actually you just did it. But maybe I didn't. Where was I?
I have the biggest proof of this.
My legs are sore. I didn't even do that much right.
Okay, so since r is a rational number, we can express it this way. Oh, he wants the positive one to be in the denominator. So we're forcing the denominator to not be a negative number. You can always represent a rational number as a quotient of two integers where the bottom one's not negative. If the rational is negative, put it in the top. If it's not negative, don't put any negatives in. You hear about that?
Yeah.
Okay. 2. Oh, that's why he used H, so he could use F and G to be our composition. Well, too late. So we use G and H. equal x to the 1 over n. Such that f of x is now equal to, I don't know which one we want to put inside, it doesn't matter, h composed with g of x. You good with that?
Now we can use our rule. Right?
Yeah. Then f prime of x is equal to our chain rule. H prime of g of x times g prime of x, right? Now just substitute what we know those are. What's h prime?
1 over.
Maybe we should have made that, it doesn't matter. We'll just do it how we have it written here. It shouldn't matter which way we do it. So the derivative of this is 1 over n times g of x to the 1 minus 1 over n. Good with that?
Okay, yeah.
Times, what's g prime of x?
M times x n minus 1.
Right? Finally do our last substitution. Maybe it wasn't good to drag it out like that. G of x is x to the m. Right? Now I'm just start doing some algebra. So first off, plug my coefficient is going to be m over n. Good. X to the m. Yeah, we could have done this with the quotient rule, which is what I'm pretty sure I did last time. That's why I'm pretty sure we did this. Anyways, let's see. X to the m. Remember, you're going to multiply. That's going to be m minus m over n. So we have x to the m minus m over n. Now remember, when you multiply terms, you add exponents. So plus m minus 1. You do that right?
Seems like the M should cancel.
Yeah, the guy says that should happen, but let's keep going with it. We've got the minus 1 that we're looking for. So now let's get these in terms of over n. So this is equal to, first off, replace my m over n with just r, times x to the, let's get a common denominator between these three terms. And that's going to be 2mn minus m over n minus 1. Did I do that right?
Shouldn't you have n minus 1 over n? Oh, no, you just times k, right? Okay, what is it?
I did the derivative wrong here. No one caught me on that. It's 1 over n minus 1, not 1 minus 1 over n.
She knows it's wrong.
Huh?
She knows
Is he
it's wrong.
blank?
Catch you on that.
Yeah, I'm blaming all of you. You're terrible.
No, she knows.
Okay. Did I screw anything else up? With this many eyes on the prom, the stapler guy should not fly. Okay, now let's do the algebra. We have m over n times x to the m over n minus m, right? Plus m minus 1. Okay. Which is equal to m over n is just r, x to the r minus m plus n minus 1. Okay, and it worked. But yeah, I'm like 95% sure we did this exact proof with the quotient rule.
I think that was the last proof.
Okay, so that's the end of 4.2. 4.3, the mean value theorem. Are you still writing stuff?
Do you remember Ariel's strength exam?
Ariel's what?
Ariel's strength exam.
Oh, yeah. Oh.
Is shampoo example of the mean value theorem?
Yeah.
In the shower one day when he was a student, and he tipped his shampoo upside down. And he watched as it slowly dripped from the top to the bottom. Thought it'd be really cool to find a way to
That has nothing to do with the mean value theorem.
find the average of how fast something.
Yeah,
They
he was
picked
trying
class that day and figured out exactly.
the average time it takes for all the shampoo to go down, and how much time it takes for all of it.
Something like that. I figured it kind of.
Anyways, mean value theorem has a very nice geometrical interpretation. The mean value theorem says if I have some function, here's some function, let's make it do this. Here's some function, we'll call this A, we'll call this B. So this right here is f of A. And this right here is, we'll call it f of B. The mean value theorem says that somewhere on this interval, well, first off, let's think about this line. Maybe green's not. Think about this line right here. What's the slope of this line? The slope of that line is f of b minus f of a over b minus a. Right?
Yeah.
The mean value theorem says that somewhere on this interval between a and b, there is a point, which in this case is probably somewhere right here. There is a point where the derivative at that point is equal to the same thing. So in other words, there's a point where the tangent line is going to be parallel to this line.
Weird.
Why is it called the mean value theorem? This is the average slope that you get if you calculate all these slopes. Over all this space, the average going up this much in this distance. Right? That's mean, average. The average value theorem, the mean value theorem. Somewhere in between, our slope is going to be that mean. Some places it's going to be lower, some places it's going to be higher. Somewhere in between, it's going to be exactly that.
Okay, what does mean again?
Average. The mean, the average. The average slope of the function from here to here is that. Right? If I were to plot Jacob's height with respect to time, and one day it was here, then it was here, then it was here, your average growth over time is captured right here. It's your average. It's the mean. It's the average change. The slope from where you started to where you ended. How much did you grow? This much. How much time did it take? This much.
So roughly.
Growth over time.
So how do you find that equation at that point?
The mean value theorem isn't telling you how to find the point. It's a guarantee that there is a point where that's true. Because this is similar to, let's see, the two that we did. We did the extreme value theorem. You remember the extreme value theorem?
Yeah.
What was the extreme value theorem?
There's always a number.
If you have a continuous function on a closed interval from A to B,
It has a minimum or it has max.
some continuous function on that interval, it's guaranteed on this interval to achieve both minimum and a maximum. Where does that happen? I don't know.
Okay.
We just guaranteed that it does do that. That was the extreme value theorem. So the mean value theorem says somewhere on the open interval, AB, now we're talking about an open interval, AB, there's a point such that the derivative at that point is equal to this number. Where is that point? I don't know. I'm just proving that there is a point where that happens. if there was another big theorem that we did that was like this.
We just proved there's
Didn't we have the extreme and it wasn't,
intermediate.
yeah.
Intermediate value theorem. Okay, there's the
Is
other
that
one.
one
Sorry.
where you have a C and an X?
The intermediate value theorem, yes, exactly. So the intermediate value theorem says if this right here is f of a, and this right here is f of b, then you're guaranteed at some point between a and b, pick a point C in between them, doesn't matter what point you pick in between them. Any point you pick between them, we're guaranteed that there's a point x naught over here, such that f of x naught equals c.
That was so stupid. Why is that cool?
Well, they're all very similar. First, we had the extreme value theorem. You reach a max and a min. Then we had the intermediate value theorem, which says you reach any value in between. Now we have the mean value theorem that says you reach the average.
Oh, it's saying that every number is that. Can you say that? That's the definition of continuity with the extreme value theorem. Or sorry, with the intermediate.
If the intermediate value theorem holds for a function, is a function continuous?
No.
I can't think of a counterexample. Yeah, I'm not sure. I'd have to think about that. Anyways, so that's the extreme value theorem. This is what we're going to be proving next time. Not the extreme value theorem. The mean value theorem. So we have the extreme value, intermediate value, and now we have the mean value theorem. Good? So there's intuition for what it will be. We'll do that next time. Get started on your homework. Make sure you understand how to derive